Hello, my friends. Welcome to Hafee Sleep, where the day's questions gently fade and the mind's deepest curiosities are invited to wander and to wonder. Have you ever lain in the quiet dark, listening to the rhythm of your own breath, and found your thoughts drifting to the biggest questions of all? What is this life? What is this universe? And what truly is time? That ticking clock on your wall, the setting sun, the memories you hold dear, the future you dream of. It all flows within this mysterious, invisible river we call time. But what is it? Where does it come from? Does it even exist the way we think it does? Tonight we're embarking on an incredible journey to find out. We'll voyage from the first ancient human observations to the bleeding edge of modern physics. We'll meet the brilliant minds who unraveled its secrets and explore theories so profound they bend the very fabric of reality. This is the story of time itself. And as we begin this journey together, I'd love to feel connected to you, wherever you are in the world, whenever you found this moment of peace. So if you're enjoying this exploration, please do hit that subscribe button and give the video a like. It truly helps this channel grow and allows me to bring more content like this to you. Most importantly, I'm so curious. Drop a comment down below and tell me two things: where you're watching from and what time it is for you right now. Are you winding down for the night? Is it the middle of the afternoon? Or are you, like me, perhaps up late, lost in thought? It's a beautiful thing to remember that we're all sharing this single vast moment in space-time together. Now, get comfortable. Close your eyes if you'd like. Let everything else melt away. And let's begin. Have you ever just stopped in the middle of a frantic day and really listened to that sound? The relentless, steady, soft ticking of a clock in a quiet room? Tick, 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 tick. It's a sound so familiar. It's the background music to our entire lives. We wake up by it, we work by it, we meet friends for coffee by it, and we eventually wind down by it. We say we don't have enough of it, or we waste it, or we save it. But have you ever truly, deeply asked yourself, what is that? What is this invisible river we're all swimming in that carries us from one moment to the next without ever pausing for breath? What is time? It feels like the most fundamental thing in the universe, doesn't it? As solid as the ground beneath our feet. You can't see it or touch it, but you can watch its effects everywhere. The fresh paint on a garden fence fading and peeling under the sun. A tiny wobbly-legged fawn growing into a majestic strong-limbed stag. The lively, smooth skin of a young face gradually mapping itself with the wise lines of a long life. Time is the great sculptor, the ultimate artist, and the final judge of all things. We are all passengers on this one-way journey, and we've built our entire civilization around measuring its passage with astonishing precision. But the real mystery, the question that has haunted philosophers and physicists for millennia, isn't how we measure it, but what it actually is in its essence. Is it a real, physical thing, a dimension woven into the fabric of the cosmos, like length and width and height? Or is it perhaps something else? A kind of illusion, a story our brains tell us to make sense of the chaotic swirl of events happening around us. Maybe it's a universal rule book, a set of laws that everything must follow. To unravel this, we need to go on a journey ourselves, a journey not through space, but through ideas. We'll visit the deepest thoughts of ancient thinkers, the brilliant revelations of the greatest scientific minds, and the mind-bending edges of modern physics where time itself begins to get wobbly. We'll ask if it had a beginning, if it will have an end, and what it might mean for you and me, right here, right now, listening to the gentle, persistent ticking of a clock. So, get comfortable. Let's step out of the current for a little while, and let's explore the great mysterious river of time. This shift in thinking, from time as a never-ending loop to a straight line with a beginning and an end, wasn't just a philosophical curiosity. It fundamentally reshaped human civilization. In a cyclical world where everything eventually returns to its starting point, the focus is on maintenance, on harmony, on playing your part in the eternal, repeating dance of the cosmos. There's a certain comfort in that. The seasons will always turn. The sun will always rise. Your actions are part of a grand, predictable pattern. But linear time? Linear time introduces something new and incredibly powerful. The idea of progress. If time is an arrow flying in one direction, then things can genuinely get better, or worse. But they change. They don't just repeat. This idea laid the groundwork for history itself, the recording of unique, non-repeating events in a sequence that leads us to where we are now. It fueled scientific discovery. Why try to understand the world and improve our lot in it if next year or next life everything just resets? Linear time gave us a timeline on which to build a narrative of improvement, innovation, and accumulation of knowledge. It gave us a destination to strive for, or a fear to avoid, but it gave the future a weight and a shape that it never had before. Now let's talk about those early devices a bit more, because their invention is a story of pure human ingenuity. The sundial seems simple, a stick in the ground, but making one accurately is a complex art. The angle of the gnomon, that's the fancy name for the stick, has to be set for your specific latitude on Earth. A sundial in Norway looks different from one in Egypt, and they had to account for the fact that the sun's apparent speed across the sky changes with the seasons, making solar days slightly different lengths. The cleverest sundials had curved hour lines to compensate for this, a beautiful marriage of art and early science. And the water clock, or clepsydra. The name comes from Greek words meaning water thief. The simplest form was just a bowl with a small hole in the bottom that you'd place in a larger bowl of water. It would fill up and sink in a specific time, alerting its owner. But they got wildly sophisticated. The Greeks and Romans developed water clocks with intricate gears and mechanisms that could ring bells, move figures, and even adjust for the different lengths of daylight throughout the year. Imagine a complex water-powered machine telling you when your time was up in a political speech. They were the high-tech clocks of the ancient world. The candle clock is a wonderfully simple and personal timepiece. You'd take a candle, make marks along its side, and light it. As it burned down, each mark would represent the passage of a certain period, an hour perhaps. King Alfred the Great of England is said to have used candle clocks to divide his day into periods of work, prayer, and rest, ensuring he used his time wisely. It was a portable, affordable, and deeply intimate way to measure the night. Of course, a draft could make your hour fly by, or a puddle of wax could make it drag on. It was imperfect, but it was yours. And then there was the hourglass, using the steady flow of sand. Its genius was its simplicity and reliability, especially at sea. On a rocking ship, a water clock would spill, and a candle could be dangerous, but an hourglass kept faithfully trickling away, helping sailors calculate their speed, and, by extension, their position on the vast, featureless ocean. The half-hour glass became iconic on ships, and the turning of the glass was a central ritual of nautical life. You can almost hear the call, "Turn the glass and mark the log." For centuries, these were the tools that governed life. Life moved at the speed of the sun and the seasons. A second was an utterly useless, immeasurably tiny fraction of time. No one needed that kind of precision. The day was divided into hours, and that was precise enough for almost everything. This created a rhythm of life that was in many ways more in tune with the natural world and the human body. You worked from sunup to sundown. You rested when it was dark. Your body's internal clock, what we now call your circadian rhythm, was perfectly synchronized with the great cosmic clock in the sky. This all began to change, slowly at first, in the monasteries of medieval Europe. The monastic day was divided into 7 or 8 canonical hours, periods for specific prayers and rituals. The first might be matins in the deep of the night, then lauds at dawn, prime in the early morning, and so on. To observe these prayers at the correct times, especially the nighttime ones, the monks needed a way to wake themselves up reliably. Bells had to be rung. This necessity was a powerful mother of invention. They began developing more sophisticated mechanical devices to automate this calling to prayer. The real breakthrough came with the invention of the verge and foliot escapement around the 13th century. Now that sounds like a complicated term, but the idea is beautifully simple. An escapement is a device that allows a clock's energy to be released in tiny, controlled, equal bursts. Imagine a gear that's being turned by a heavy weight on a rope. If you let it, the weight would just plummet to the ground and the gear would spin wildly. Not very useful for telling time. The escapement is like a little gatekeeper. It locks and unlocks the gear, allowing it to turn one tooth at a time. Tick, lock, tock, unlock. Tick, lock, tock, unlock. The foliot was a horizontal bar with weights on it that swung back and forth, regulating the speed of this locking and unlocking. By adjusting the weights, you could make the clock run faster or slower. This was the heart of the first mechanical clocks. They were massive, iron-framed beasts, installed in the towers of churches and cathedrals. They didn't have faces or hands at first. Their entire purpose was to ring a bell, to call the community to order, to prayer, to market. They were the communal heartbeat of a town. And what a sound that must have been. For the first time in history, the rhythm of human life was not dictated by the sun or the seasons alone, but by a human-made machine. The clock tower became the center of civic pride and power. The clock's bell could warn of danger, call citizens to meetings, mark the start and end of the workday. It was a symbol of order and control. Time was becoming a communal resource, something to be managed and shared by the entire society. This was the first step on the road to our modern, hyper-scheduled existence. As the technology improved, clockmakers added faces and hands. First, just an hour hand. Minutes were still too fine a detail to measure. But as craftsmanship improved, the minute hand was added, and finally, in the 18th century, the second hand. Time was being sliced into ever thinner, more precise segments. The next giant leap came from a familiar frustration. How do you keep accurate time on a ship being tossed about on the ocean? This wasn't just a matter of convenience. It was a matter of life, death, and empire. To know your position east or west, your longitude, you need to know the exact time back at your home port. As the Earth rotates, time and position are directly linked. Every 4 minutes of time difference equals 1 degree of longitude. So, if you have a clock on your ship that's set to London time, and you observe the sun to find that your local noon happens when that clock says 2 Homao p.m., you know you are 2 hours, or 30 degrees, west of London. The problem was that the pendulum clocks of the day were useless on a rolling ship. Temperature changes and humidity would warp the wood and metal, throwing them off. The British government, desperate for a solution, offered the Longitude Prize, a king's ransom of $20,000, to anyone who could build a marine chronometer that could keep accurate time at sea. The man who finally cracked the problem was a self-taught Yorkshire carpenter and clockmaker named John Harrison. He devoted his entire life to the quest. His story is one of obsession, brilliance, and sheer stubbornness. He built a series of increasingly incredible clocks, known as H1 through H4. He abandoned the pendulum, using instead a spring-based mechanism. He invented the bimetallic strip to compensate for temperature changes, and the caged roller bearing to counteract the motion of the ship. His final masterpiece, H4, looked like a large pocket watch and was a miracle of precision engineering. After decades of struggle, political interference, and tests, Harrison's chronometer finally proved itself. It had won the prize. For the first time, sailors could know their exact position on the featureless ocean. It made global navigation safe and reliable, shrinking the world and cementing the dominance of seafaring nations. It was the final step in liberating time from the heavens. Now, the most accurate time in the world could be carried in your pocket, anywhere on Earth. This changed society forever. Before mechanical clocks, time was fuzzy. Meet me when the sun is at its highest was a vague appointment. But with clocks, time could be standardized and precise. Meet me at noon, sharp. Work could be regulated. Factories could run on shifts. Trains could have schedules. The entire pace of modern life, with its deadlines and appointments, was born from the tick-tock of the mechanical clock. Time became a commodity. Time is money, Benjamin Franklin would later say, and we've been racing against the clock ever since. Our measurements became more and more precise. We divided the day into 24 hours, the hour into 60 minutes, the minute into 60 seconds. But what is a second? For a long time, it was defined as 1 over 86,400 of a mean solar day. But scientists discovered a problem. The Earth's rotation isn't perfectly constant. It's very slightly slowing down due to the gravitational tug of the moon and other factors. A day is getting longer by a tiny fraction of a second every century. So, a second based on the Earth's rotation is like trying to measure the length of a room with a rubber band that keeps stretching. We needed a better, more fundamental standard. We needed to find a clock that never, ever changed. And we found it not in the heavens, but in the atom. In 1967, science officially redefined the second. It is no longer based on astronomy, but on physics. A second is now defined as the time it takes for a cesium-133 atom to vibrate exactly 992,631,770 times. Think about that number. 9,192,631,770 vibrations. That is the new heartbeat of our world. Atomic clocks, which use this principle, are so precise they will not gain or lose a second in over 100 million years. We can now measure time with an accuracy that is almost incomprehensible. So we got very, very good at measuring time's flow. But we still hadn't answered the original question. What is time? This was the world that Isaac Newton was born into. A world where timekeeping was becoming precise and mechanical. It's no wonder that he saw the universe itself as a perfect, giant, mechanical clockwork built by God, the divine clockmaker. In this model, time was the steady, constant, unchanging beat against which the gears of the cosmos turned. It was absolute, universal, and true. If you could somehow stop all motion in the universe, Newton believed, time would just keep on ticking, an impartial referee. Before Einstein, the world ran on the physics of Sir Isaac Newton, and Newton's view of time was the one most of us intuitively have. He saw time as absolute, true, and mathematical. It flowed along at a constant rate throughout the universe, entirely independent of anything else. It was like a master clock for the cosmos, ticking away in the background. A second on Earth was a second on Jupiter, was a second in a galaxy far, far away. Space was the stage, and time was the universal clock, and everything happened against this fixed, unchanging backdrop. This made perfect sense and explained the motion of planets and apples falling from trees beautifully. It's a very comforting idea. This view is so intuitive. It feels right. It's the way we still experience time in our daily lives. We set our watches and assume that everyone, everywhere, in the entire universe is experiencing the same now as us, that a second for us is a second for an alien on a planet in the Andromeda galaxy. This is the comforting, solid ground of Newtonian physics. It explained the fall of an apple and the orbit of the moon with breathtaking elegance and power. It made the universe knowable and predictable. But Einstein realized something was wrong with this picture. The problem started with light. Scientists had discovered that light always travels at the same speed, about 108,6,282 miles per second in a vacuum. It doesn't matter who is measuring it or how they are moving. If you're standing still and you measure the speed of a beam of light, you get 186,282 miles per second. If you're in a spaceship racing towards that beam of light at half the speed of light and you measure it, you would think, intuitively, that the light should be approaching you at its speed plus your speed. But you don't. You still measure it as 186,282 miles per second. It's completely counterintuitive. How can that be? Einstein's brilliant insight was to take this bizarre fact seriously and follow its logic to the most incredible conclusions. In 1905, with his special theory of relativity, he declared that the speed of light is the one constant in the universe. Everything else, space and time themselves, must adjust to keep the speed of light constant for all observers. This was the key that unlocked a new reality. Let's dive deeper into this, because this idea is the real heart of the revolution. The moment our intuition about the universe breaks down and we have to build a new one from the ground up. It feels like a magic trick, but it's a fundamental property of reality. And to really get it, we need to walk through it slowly, step by step. First, we have to firmly plant our feet on the solid ground of that one non-negotiable rule. The speed of light is constant for everyone. It's the ultimate cosmic speed limit, and it's enforced not by a police officer with a radar gun, but by the very fabric of space-time itself. Nothing with mass can ever reach it, and light, which has no mass, must always travel at it. This isn't a suggestion, it's the law, and this law forces the universe to make some incredible adjustments. Now let's flesh out our thought experiment with the twins, Astra and Terra. We need to make it more real, to picture it happening. Imagine Terra standing on a spacious green field on Earth, a special clock beside her that displays not just the time, but the date, and even her biological age. It's a beautiful, sunny day. Astra gives her sister a final hug, her spacesuit crisp and white, and walks up the ramp into her sleek silver ship, the Paradox. The hatch closes with a soft hiss. The Paradox doesn't roar away like a rocket. It uses some futuristic silent propulsion system. It just lifts off the ground, hovers for a moment, and then, with a faint shimmer of distorted air, it's gone, accelerating to a significant fraction of light speed almost instantly. Let's say it's going to 99.5% the speed of light. From Tara's perspective on the ground, she watches the ship become a speck, then vanish into the starry blackness, heading towards a star we'll call Helios, which is precisely 10 light years away. So, Tara does the math. The ship is going almost the speed of light. To travel 10 light years, it should take just a hair over 10 years to get there, and another 10 years to get back. So, she settles in for a 20-year wait. She marks her calendar. She tends the garden around the launch site. She grows older. She might get married, have children, pursue a career. Her hair might show streaks of silver. She lives her life, all the while looking up at Helios, knowing her sister is out there. For her, 20 real, tangible Earth calendar years pass. Now let's jump on board the Paradox with Astra. What does she experience? The initial acceleration is immense, pressing her into her seat, but once the ship levels out at a constant 99.5% light speed, she feels normal. There's no sensation of immense speed. You don't feel speed, you only feel acceleration. If the windows were covered, she'd have no way of knowing she was moving at all. This is Einstein's first postulate in action. The laws of physics inside her ship are the same as if she were at rest. She looks at her own ship's clock. It's a perfectly functioning, precise timepiece. To her, it ticks along normally. She eats, sleeps, reads books, works out in the ship's gym to avoid muscle atrophy. She lives her life. She also has a powerful telescope pointed at Earth. What does she see? Something very, very strange. Because she is moving away from Earth at near light speed, the light waves coming from Earth are getting stretched out. This is the Doppler effect, similar to how the siren of a police car sounds lower in pitch as it races away from you. But for light, stretching the waves makes them redder. So, Astra sees Tara living her life in slow motion and bathed in a red glow. Every action, every wave from her sister is drawn out and sluggish. From Astra's perspective, time on Earth is crawling. She also looks ahead at her destination, the star Helios. Because she is racing towards it, the light waves from Helios are compressed. The Doppler effect here works in reverse, shifting the light blue. And more than that, the universe ahead of her appears compressed. The distance to Helios isn't 10 light years anymore. Because of her incredible speed, length in the direction of her motion has contracted. This is the other side of the relativistic coin, called Lorentz Fitzgerald contraction. In her reference frame, the journey might only be, say, 1 or 2 light years long, so she gets there much quicker by her own measure of time and distance. Let's say, for her, the trip to Helios only takes 1 year of her ship time. She arrives, spends a day taking pictures, and then turns around for the journey home. Now, on the return trip, racing back towards Earth, the effects flip. Now Earth's light is compressed, blue shifted, and she sees Tara's life flashing by in fast forward. The journey back again takes only 1 year of her time. So, her total journey time, by the clock on her ship and by her own biological aging, is 2 years. She's 2 years older. She's had 2 years of experiences, 2 years of meals, 2 years of reading. Meanwhile, back on Earth, 20 full years have passed. Tara is 20 years older. The Paradox lands back on the green field. The hatch opens. Astra walks down the ramp, still young, her body and mind having only experienced a 2-year journey. She expects to see her twin as she left her. Instead, she's greeted by a woman who is noticeably middle-aged, with laugh lines around her eyes and a maturity that only decades can bring. They are no longer identical twins. Astra has, in every meaningful sense, traveled 18 years into her sister's future. This is the famous twin paradox, and it's not a paradox at all within relativity. It's a real, predicted effect. The key to understanding why it's not a contradiction lies in symmetry, or rather, the lack of it. The situations of the two twins are not the same. Terra remained in a single inertial frame of reference, ignoring the Earth's rotation and orbit for simplicity, which are slow enough to not change the result much. She felt no forces. She was, for all intents and purposes, at rest. Astra, however, did not stay in one inertial frame. To turn around and come back, she had to accelerate. She had to fire her engines to slow down, stop, and then accelerate back towards Earth. Acceleration is absolute. You can feel it. It was during these periods of acceleration that the two reference frames became truly distinct. The person who feels the acceleration is the one whose experience of time is truly altered. So, the theory consistently predicts that Astra, the one who undertook the journey with its changes in motion, is the one who ages less. This isn't just a thought experiment. We have direct, irrefutable proof that this happens all the time, right above our heads. Let's talk about muons. These are tiny subatomic particles, sort of like heavy electrons, that are created when cosmic rays from the sun hit the upper atmosphere. They are incredibly unstable and decay into other particles in just 2.2 microseconds, millionths of a second, on average. Even if they were traveling at the speed of light, in their brief little lives, they could only travel about 0.6 kilometers before blinking out of existence. They are created about 10 kilometers up in the atmosphere. And yet, vast numbers of them are detected here on the ground, in laboratories. How? How did they travel 10 kilometers when they should only make it 0.6? There are two ways to explain this, and both are correct depending on your point of view, and both are proof of relativity. From our perspective on the ground, the muons are moving so close to the speed of light that their clocks are running incredibly slowly. Their internal decay timer is dilated. What is 2.2 microseconds in their rest frame is stretched out into many microseconds from our point of view. Plenty of time for them to travel the 10 kilometers down to us before decaying. From the muon's perspective, it's not living longer. In its own reference frame, it still decays in 2.2 microseconds. But because it is moving so fast relative to us, the distance from the upper atmosphere to the ground is not 10 kilometers. It is length contracted to a much shorter distance. It only has to travel, from its point of view, a few hundred meters, which it can easily do in its short lifetime. Either way you slice it, whether time is stretching or space is contracting, the conclusion is the same. The muons reach the ground. And this is not a theory. It's a measurable, everyday fact for particle physicists. Our GPS satellites have to account for this every single second. The atomic clocks on those satellites, moving at about 14,000 kilometers per hour relative to the Earth, run slower due to their speed, special relativity, but also run faster because they are in a weaker gravitational field further from Earth, general relativity. The net effect is that they gain about 38 microseconds per day. If the engineers didn't constantly correct for this, the GPS system would accumulate errors of several kilometers per day making it useless. So, every time you use your phone to navigate, you are personally, directly using Einstein's theory of time dilation. You are relying on the fact that time on a moving satellite is different from time on your phone. So time is not a universal drumbeat. It's a rhythm that changes with your dance through space. The faster you move, the slower your personal rhythm becomes relative to someone moving more slowly. It's a cosmic compromise, a negotiation that the universe undertakes to ensure that no matter how fast you are going, when you measure the speed of a beam of light, you always get the same answer. It's the price of admission for a universe with a fixed speed limit, and it means that travel into the future isn't just science fiction. It's a guaranteed, proven consequence of the laws of physics. We already do it, on a tiny scale, every day. We just don't have the technology yet to do it on the dramatic scale of Astra and Terra. But the universe, in its silent mathematical way, has already given us permission. The future is, quite literally, a place you can travel to. But that's not all. Einstein also showed that time is deeply intertwined with space. He combined them into a single, four-dimensional fabric called space-time. Think of it like a trampoline. The fabric of the trampoline is space-time. If you place a heavy bowling ball in the middle of the trampoline, it creates a deep dip or curve in the fabric. Now, if you roll a marble near the bowling ball, it won't go in a straight line. It will curve around the dip, orbit the bowling ball. The bowling ball's mass has warped the space-time around it. In our universe, the sun is the bowling ball. Its mass warps the space-time around it, and Earth is the marble, following the curved path of that warped space-time. We feel that curved path as gravity. Let's settle in and really unpack this next layer of the mystery, because what we're about to delve into is perhaps even more profound than the strange effects of speed. We've seen how motion warps time. Now, we're going to see how gravity, the most familiar force in our daily lives, does the exact same thing. After he published his special theory of relativity in 1905, which dealt with constant, steady motion, Einstein was deeply bothered by a problem. His new theory beautifully included everything except for gravity. Newton's description of gravity, as a mysterious instantaneous force acting at a distance, clashed violently with his new ideas. According to special relativity, nothing, not even information, can travel faster than light. So how could the sun, 93 million miles away, instantly tell the Earth how to move? How could it reach out across that vast emptiness and tug on us? It was as if the sun was whispering a command to the Earth, and the Earth was hearing it at the exact same moment, which is impossible if information is limited by the speed of light. Einstein spent the next 10 years wrestling with this problem. His breakthrough moment is legendary in the history of science. He called it the happiest thought of my life. He imagined a man falling from a roof. In that moment of free fall, the man would feel weightless. If he dropped a hammer and a feather, they would float beside him, not falling relative to him. He realized that a person in free fall doesn't feel gravity. They are, in effect, in a state of zero gravity. Now imagine this man is in a windowless elevator car. If the elevator cable is cut and the car plummets downwards, everything inside floats. The man, the hammer, the feather. They all hover as if in deep space. There is no experiment he can do inside that falling box to prove he is in a gravitational field. Now, imagine another man in an identical windowless elevator car, but this one is actually out in the vacuum of deep space, far from any planet or star. This man also floats. He also feels weightless. He also sees the hammer and feather hover beside him. Einstein's genius was to realize that there is no difference between these two situations. The man in the falling elevator and the man in the elevator in deep space are physically identical. There is no way to distinguish between being in a gravitational field and being in an accelerating frame of reference. This is the equivalence principle. The laws of physics in a uniform gravitational field are identical to the laws of physics in a uniformly accelerating frame of reference. Let's test this. Imagine you are in a rocket ship out in space, far from gravity. If the ship is coasting with its engines off, you float weightlessly. Now, if the ship's engines fire, and it begins to accelerate at a constant rate, let's say at 9.8 meters per second squared, which is the acceleration due to gravity on Earth, what happens? You are pushed against the floor of the ship. If you stand on a scale, it registers your weight. If you drop a pen, it falls to the floor. From inside this windowless, accelerating rocket, everything behaves exactly as if you were sitting still in a rocket parked on the launch pad on Earth. You would swear you were feeling the gravity of a planet. This equivalence is the key that unlocked general relativity. Gravity, Einstein concluded, is not a force in the traditional sense. It is not a mysterious pull. Instead, it is a consequence of the shape of space-time itself. Massive objects, like the sun, the earth, you, me, warp the four-dimensional fabric of space-time around them. Let's go back to our trampoline analogy, but let's really flesh it out this time. Imagine space-time as a vast, taut, elastic sheet. This is our stage. Now, place a heavy bowling ball in the center. What happens? It creates a deep, curved depression in the sheet. This is the warping of space-time by mass. Now, take a marble and roll it past the bowling ball. Instead of going in a straight line, the marble will curve inward, following the contour of the depression. It might even spiral around the bowling ball, or, if rolled with just the right speed, go into a stable orbit around it. From a bird's eye view, it looks like the bowling ball is exerting a force on the marble, pulling it in. But that's an illusion. There is no force. The marble is simply following the straightest possible path through the curved geometry of the sheet. In our universe, that curved path is what we perceive as the force of gravity. The Earth isn't being pulled by the sun. It's simply following a straight line path, called a geodesic, through the curved space-time created by the sun's immense mass. Gravity is geometry. Now, here is the crucial part for time. If space-time is a single woven fabric, then you cannot warp space without also warping time. The curvature affects everything that exists within space-time, including the flow of time itself. The deeper the gravity well, the more severe the warp in space-time, the slower time flows. Imagine two identical, incredibly precise atomic clocks. Let's put one clock here at sea level. Let's put the other clock on the top of a very tall mountain, say Mount Everest. Now the clock at sea level is deeper within Earth's gravity well. The space-time there is more curved. The clock on the mountain is further from the Earth's center, in a region where space-time is slightly less curved. According to general relativity, the clock at sea level should tick more slowly than the clock on the mountain. And this is exactly what happens. The difference is tiny, a few billionths of a second over a lifetime, but it is measurable with our best atomic clocks. In fact, this effect has been tested countless times. In one famous experiment in 1976, physicists launched a super-accurate atomic clock on a rocket to a high altitude and compared its time to an identical clock on the ground. The clock in the weaker gravity high up in the sky ran faster, just as Einstein predicted. This is not a theoretical curiosity. It is an engineering reality that we must account for. This brings us to that wonderful, almost absurd conclusion. Your feet are younger than your head. Think about it. You are standing up. Your head is about 6 feet further from the center of the earth than your feet are. Therefore, your feet are in a very slightly stronger gravitational field than your head. The space-time at your feet is very slightly more curved. Therefore, time at your feet flows very, very slightly more slowly than time at your head. Over the course of your entire life, your feet will have experienced a tiny, tiny bit less time than your head has. They are, in a literal sense, younger. Now, the difference is fantastically small. We're talking about a difference of maybe a few hundred billionths of a second over an 80-year lifespan. You could never possibly perceive it. But the point is, the effect is real. The mathematics of general relativity demands it, and our most precise instruments confirm it. It shows us that time is not just a universal reading. It's a local experience, intimately tied to the geometry of the space you are in. The effects become truly dramatic when we look at the most extreme objects in the universe, neutron stars and black holes. A neutron star is the collapsed core of a giant star, a sun crushed down into a ball the size of a city. It has immense gravity. If you could somehow stand on the surface of a neutron star, you can't. You'd be instantly flattened into a thin paste. Time would flow much, much slower for you relative to a distant observer. An astronaut orbiting the neutron star would see your movements as if you were stuck in super slow motion. And then, there's the ultimate gravity well, a black hole. At the center of a black hole lies the singularity, a point of infinite density where the warp in space-time becomes infinite. At the boundary around it, the event horizon, the warping is so extreme that anything that crosses it, including light, can never escape. And at the event horizon, from the perspective of a distant observer, time effectively stops. If you could watch a clock fall into a black hole, you would see its ticks get slower and slower, wider and wider apart, until the final tick, as it crosses the horizon, takes forever. The clock would appear to freeze at the edge of time itself. Of course, for the person carrying the clock into the black hole, their own time would feel normal. They would cross the event horizon without noticing anything special at that moment, until the tidal forces. But that's another story. But to the outside universe, their timeline would simply end, stretched into infinity. This is the ultimate expression of gravitational time dilation. So, every single second of our lives, we are immersed in this flexible dynamic fabric. The gravity of the Earth, the Sun, the Milky Way galaxy, all gently tug and warp the space-time around us, subtly influencing the rate at which our personal clocks tick. We are like fish swimming in an ocean of curved space-time, rarely noticing the water itself. But with the brilliant light of Einstein's theories, we can finally see it. We understand that the force that keeps our feet on the ground is the same force that gently slows the ticking of our hearts relative to the stars. It is a unified, beautiful, and deeply strange picture of reality, where time and space are not just a stage, but active, flexible players in the cosmic drama. This completely shatters the Newtonian idea of a universal clock. There is no now that applies to the entire universe. Your now is relative to you. What is happening now for you might be in the past or the future for someone else moving at a different speed or in a different gravity well. Einstein's work showed us that time is a flexible, malleable dimension. Woven together with space, into the fabric of the cosmos. It's a dimension we can move through in one direction only, forward, but its rate is not fixed. It's a local phenomenon, not a global one. This brings us to one of the biggest questions of all. Did time itself have a beginning? Of course, yes. Let's sit with this one for a while, because this is perhaps the most profound and mind-bending destination on our journey. We've traveled from the sundial to the atom, from Newton's absolute stage to Einstein's flexible fabric. We've seen that time is malleable, personal, and shaped by speed and gravity. But now we arrive at the ultimate question. Did it have a starting line? Did the great river of time itself have a source? And the answer, as best as we can tell, is a whisper that slowly grows into a thunderous yes. To understand why, we have to rewind the cosmic movie. Not just a little, but all the way back. And our guide for this part of the story is, once again, the Hubble telescope. In the 1920s, an astronomer named Edwin Hubble was using the most powerful telescope in the world at the Mount Wilson Observatory in California. He was studying strange, fuzzy patches of light in the sky called nebulae. The prevailing wisdom was that these were just clouds of gas within our own Milky Way galaxy. But Hubble, by studying a certain kind of star whose true brightness he knew, made a shocking discovery. These nebulae weren't inside our galaxy. They were impossibly far away. They were entire other galaxies, islands of stars unto themselves, separated by a vast, mind-numbing ocean of empty space. The universe was instantly and dramatically made thousands of times larger than anyone had imagined. But that was just the first act of Hubble's revolution. By analyzing the light from these distant galaxies, he noticed something even more bizarre. The light was shifted toward the red end of the spectrum. This is the famous redshift. Now, we mentioned the Doppler effect earlier with sound, a siren sounding lower pitched as it moves away. For light, the same principle applies. A redshift means the source of the light is moving away from us. To Hubble's astonishment, every galaxy he looked at, except for a few very nearby ones, showed a redshift. And the farther away the galaxy was, the greater its redshift. The farther a galaxy was, the faster it was receding from us. The universe wasn't static. It was expanding. It was growing, like a loaf of raisin bread rising in the oven. Imagine the dough is the fabric of space itself, and the raisins are galaxies. As the dough expands, every raisin moves away from every other raisin. A raisin in one part of the loaf would see all other raisins speeding away from it, and the raisins farthest away would appear to be moving the fastest. This is exactly what Hubble saw. There was no center. From every point, the view would be the same. Everything is rushing away from everything else. Now, if the universe is expanding now, what does that imply about the past? If you run that movie backwards, what do you see? All the galaxies move closer together. The universe gets denser, hotter, and smaller. Rewind further. All the matter and energy in the cosmos gets compressed into a smaller and smaller volume. Further still. Eventually, you reach a point where the entire observable universe, all hundreds of billions of galaxies, each with hundreds of billions of stars, is compressed into an area smaller than the period at the end of this sentence, a point of infinite density and temperature. This is the moment we call the Big Bang. This name is a bit misleading. It makes us picture a conventional explosion, like a bomb going off in a dark, empty room. But that's not it at all. The Big Bang was not an explosion in space. It was the rapid expansion of space itself. There was no outside for it to explode into. There was no before for it to happen in. Space, time, matter, and energy, all of it, came into existence at that moment. This is the crucial part that is so hard to wrap our heads around. We are creatures of time. Our language, our logic, our very consciousness is built on the concepts of cause and effect, of before and after. So, it is almost a biological imperative for us to ask, okay, but what happened before the Big Bang? But according to our best physics, that question might be a category error. It's like asking, what sound does the color purple make? Or, how much does happiness weigh? The question applies concepts to a context where they no longer have meaning. Before is a temporal word. It requires the existence of time. If time itself began at the Big Bang, then the concept of before simply does not apply. There is no temporal shelf on which to place a before the Big Bang event. It's like asking what is north of the North Pole. Once you're at the North Pole, every direction is south. There is no north of it. The North Pole is the boundary of that concept. Similarly, the Big Bang is the temporal boundary of our universe. The great physicist Stephen Hawking used a wonderful analogy. Think of the beginning of the universe like the South Pole of the Earth. You can ask what is south of the South Pole, but the question doesn't make sense. The South Pole is the southernmost point. The laws of geometry and navigation break down there as a reference. The Big Bang is the South Pole of time. There is no time south of it. This moment of beginning is what physicists call a singularity. A singularity is a point where our current laws of physics, specifically Einstein's theory of general relativity, break down completely. The mathematics produces terms that become infinite density, infinite temperature, infinite curvature. In science, an infinity is usually a sign that your theory is incomplete, that it's reached the edge of its usefulness, and you need a new, deeper theory to take over. It's like an old map that just says, "Here be dragons," beyond a certain point. We believe that a theory of quantum gravity, a theory that successfully merges the large-scale world of gravity, general relativity, with the small-scale world of particles, quantum mechanics, will be needed to understand what truly happened at time zero. This theory might allow us to peer, conceptually, at the moment of the Big Bang itself, or perhaps even suggest that there was no true singularity, but rather a bounce or a transition from a previous state. Some theories, like the cyclic model or conformal cyclic cosmology, propose ways in which the universe might go through endless cycles of expansion and contraction, a Big Bang, followed by a big crunch, followed by another Big Bang. Others, like the multiverse theory, suggest our Big Bang was just one bubble inflating in a vast, eternal, and larger meta-universe where time operates differently. String theory and loop quantum gravity offer visions where the concepts of space and time emerge from something more fundamental, like threads vibrating in higher dimensions or loops of quantum field. These are all fascinating and speculative ideas, but for now, based on the overwhelming evidence we have, the observed expansion of the universe, the cosmic microwave background radiation, the leftover heat from the Big Bang itself, which we can still detect as a faint static coming from all directions in the sky, and the abundance of light elements, the standard model of cosmology holds that our universe, and with it, the dimensions of space and time as we know them, began 13.8 billion years ago. So when we say time started with the Big Bang, we are making the best statement we can with our current knowledge. We are saying that the chain of cause and effect, the sequence of moments that we can meaningfully talk about, the history of everything we can observe and measure, has a definitive starting point. It's the ultimate horizon. We can sail right up to a tiny, tiny fraction of a second after it. We can model the universe when it was just a hot, dense soup of fundamental particles, a mere 10 to power minus 43 seconds old. That's a decimal point followed by 42 zeros and then a 1, the Planck time. But at the moment of the singularity itself, our maps fail. The dragons are real. So where does this leave us? We have explored time from the ancient sundials to the atomic clocks, from Newton's absolute time to Einstein's flexible space-time, from the Big Bang to the possible end of everything. We've seen that time is not a simple thing. It's a measure of change, a dimension of the universe, a relative experience, and perhaps even a quantum illusion. It might be granular, it might be part of a fixed block, and its arrow might be defined by the increasing messiness of the cosmos. But perhaps the most beautiful and humbling thought is this: we are time. The very atoms that make up our bodies were forged in the hearts of ancient stars that died billions of years ago. We are literally stardust, and that stardust has been on an unimaginable journey through time to come together and form us. Our consciousness is the universe's way of experiencing itself across time. We are the universe's memory. When we look up at the stars on a clear night, we are not just looking out into space, we are looking back in time. The light from those stars has traveled for years, decades, centuries, even millennia to reach our eyes. We are seeing them not as they are now, but as they were when that light began its journey. The night sky is a vast time machine, a museum of cosmic history. And in our own lives, time is the substance of our story. It's the canvas on which we paint our joys, our sorrows, our loves, and our losses. It is the most precious resource we have, because it is the one thing we can never get more of. We can't save it. We can only spend it. And how we choose to spend it is the very definition of our lives. The physics of time is complex and mysterious, but the human experience of time is simple and profound. It is the feeling of a child's hand in yours, knowing that all too soon that hand will be grown. It is the comfort of a familiar memory and the excitement of an unknown future. It is the bittersweet beauty of a moment, knowing it will pass. So, the next time you hear that quiet, persistent ticking of a clock, don't just hear a countdown. Hear it as a heartbeat, the heartbeat of the universe, the rhythm of existence. It's the sound of space itself breathing in and out, the sound of galaxies spinning, of stars being born and dying, of history unfolding. It's the sound of your own story being written, one precious, irreplaceable moment at a time. We may never fully understand what time is, but we can always appreciate the incredible, mysterious, and beautiful journey it allows us to take. And that, perhaps, is enough. And so, my friends, we find ourselves back at the quiet end of our journey. Having ventured from the first human gaze at the shifting shadows to the very edges of the cosmos, where time itself becomes soft and malleable. We've seen that time is not a master, but a companion, not a rigid ruler, but a flowing river. It's the sculptor of mountains and the keeper of our stories. It's a dimension to be traveled, a rhythm to be lived, and a mystery that, perhaps, is the very essence of our experience. But the most beautiful part, your time right now is a gift. However you choose to spend it, in curiosity, in rest, in connection, is a unique and irreplaceable moment in the history of the universe. I truly hope this journey has given your mind a peaceful place to wander. If it did, and you'd like to join us for more explorations into life's great mysteries, please consider subscribing to Hafee Sleep and hitting that like button. It helps this community of curious minds grow. And before you go, I'd love to hear from you. Let's create a beautiful map of our shared moment. Leave a comment and tell me where in the world you are and what time it is for you as you listen to this. It's a wonderful reminder that we are all, right now, under the same starry sky, riding the same river of time together. From all of us here at Hafee Sleep, thank you for spending your precious time with us. Wherever you are, whatever the hour, we wish you peace, we wish you wonder, and we wish you a deep and restful sleep. Good night.